Hi class, welcome back to part 2 of chapter 1. I moved my me around so that I can show you I'm not blocking any of the things I want to talk about. Now here is proper soda. See this giant molecule right here? That's sugar. Yum. Actually no, I'm wrong. This is caffeine. Yum. This is sugar. Yum. This is CO2 and this is water. Over here you can see what individual lead atoms look like. They are not bonded together. They're telling you a little bit of a lie here. Either that or this picture came from like the 1980s when we still had lead in pencils, because now we have graphite, and graphite has a bond. And then this is DNA. I think they are showing it from this man's skin. So you can see it's a double helix. Our very last chapter we spent some time talking about DNA because it comes back up in micro. So here are some popular conceptions that limit the idea of chemicals. People will say, I don't like chemicals, but what they really mean to say is they don't like chemicals that are toxic, poisons, or pollutants. So distinguish, because the air we breathe is mostly nitrogen, N2, it's a chemical. It's only 18% oxygen. That can change based on where you are, but it's typically around 18%. And it's O2. And then there's a lot of CO2 in air, there's trace argon, and there's trace other gases. The water we drink is H2O, chemicals. It's also full of ions, which we need because we run off of ions. Chloride, calcium, potassium. Toothpaste, Tylenol, toilet paper, everything is a chemical. Chemistry seeks to explain the properties and behavior of chemicals by helping us to understand the molecules. So they go down to the molecular level, which your physiology textbook hasn't done. So this is newer. They go down to the molecular level to try and explain chemicals. Feynman, who went here in Pasadena, he went to the California Institute of Technology, which is still ranked #1 for chemistry. It always has been. Every now and then MIT slips in, but it's usually California Institute of Technology. He noted that all things are made of atoms. That's legit. Until you get into outer space, all things are made of atoms. So here's a good simple definition of chemistry. Chemistry is the science that tries to understand how matter behaves by studying how atoms and molecules behave. We opened with this actually. The next thing I want to talk about, which is very important because you're going to use it every day as a nurse, every day as a healthcare provider, every day if you go on and become a doctor or even work in public health, you will use the scientific method. The scientific method is a way to understand the world, and it's a very linear method of looking at things. It stands in contrast to ancient Greek philosophies and medieval applications that emphasize reason. So they would just go, this is what I think is happening. The scientific method actually relies heavily on experiments. So the first thing that might happen in the scientific method is you make an observation. Let's say today you wake up and someone leaves a container on your front porch, and it's a clear liquid, and you have no idea what it is. So that's your first thing that you've done. You've made an observation. You call someone up and you're like, a clear liquid was left on my porch. And then whoever you're talking to is going to be like, what is it? And you're going to say, I don't know, maybe it's alcohol, maybe it's water, maybe it's a poison. All of these are hypotheses. And eventually your neighbor or you are going to say, let's send it to the police and let them figure it out. And the police will run experiments on it. And the police may put it through a mass spectrometer, and a mass spectrometer will break it into its individual atoms. And the police may find, oh, this is 2 hydrogens for every 1 oxygen. And then they'll say, someone just left water on your doorstep. And that would be a law. But we don't know why someone left water on the doorstep, so we don't have a theory. If they said someone left water on your doorstep because they knew that your water was going to be shut off between 1 and 3 today, and they wanted you to have some water because they were being thoughtful, now they've given you a because. That's a theory. But unless they give you a because, it's a law. A law is much weaker than a theory. A law is a brief, keyword brief, statement where a theory has multiple parts and it explains why. So hypotheses, laws, and theories must be tested and validated. They're often changed. Everything can be revised. Between the years of 1743 and 1794, Antoine Lavoisier, a French chemist, made an observation. He thought that if you burn something, it does not disappear. Prior to that, everyone thought if you burn something, it's just gone. You can just burn something, it's gone. But Lavoisier said, no, it is not, and I'm going to prove it. Combustion means burning. So Lavoisier got very dressed up, and he went to his laboratory. And apparently chemists were like hot commodities then, because look at him. He's like, he has his wife hanging out with him in the laboratory, or his girlfriend, I'm not even sure. And right here is where he's conducting his experiment in his very formal attire. It's like they had a dance to go to afterwards. And he measured the mass of the contents, maybe it was just an oil, before burning. And then he measured the mass after burning, and he found that there was no change in mass. So he decided, you know what, I don't think when you burn something it disappears. I think it goes into a different state. And we now know that that state is CO2 and H2O. That's what we'll talk about later. When you combust something like oil, CO2 and H2O is the common thing. So Lavoisier was right. He developed the law of conservation of mass, which states in a chemical reaction, matter is neither created nor destroyed. In a chemical reaction, in a nuclear reaction, which is rare, matter is created and destroyed. But in a chemical reaction, it is not created or destroyed. This law is true, but Lavoisier did not know why, so that's why it's a law. If he knew why, if he knew that it was forming CO2 and H2O, then his law would have turned into a theory because he could say because. But he didn't know why. So it actually was Dalton, way later, who just proposed the law of conservation of mass is due to the fact that all matter is composed of small indestructible particles called atoms, and they are rearranging. Dalton was almost right. He was wrong about the indestructible. Atoms can be destroyed. Certain atoms, like uranium and plutonium, are very unstable and they're easy to destroy, and it's the nucleus that's destroyed, and it causes a cataclysmic reaction, which need a lot of it. But thankfully, they are very rare, these nuclear reactions. So the bulk of the reactions that we will talk about in this class, in every single chapter, will be a chemical reaction. But Dalton's idea was called a theory because he explained the why of Lavoisier's law, which just had a brief statement of what was happening.